Welcome to the fourth video lecture in our series of video lectures for our 11th class time. As your text mentions, cis and trans isomers are cyclic diastereomers. So what do I mean by that? Let's take this example of cis R1-bromo S2-chloro cyclopentane. Of course, there's a mirror image of this molecule, which would be the cis S1-bromo R2-chloro cyclopentane. We know that the two halogen substituents are cis. They're on the same side of the plane formed by that five-membered ring. Now, if we look at a trans stereoisomer, either the trans R1-bromo R2-chloro cyclopentane or the trans S1-bromo S2-chloro cyclopentane, either of those trans stereoisomers are going to be diastereomers to this molecule as well as to this one. So cis and trans isomers are cyclic diastereomers. Of course, these two trans stereoisomers, the RR and the SS configuration, are related as enantiomers. How about a molecule with three stereocenters? We only get more and more complicated. So you could think about an image, SSS, SSR, SRR, or SRS. And of course, the mirror image would be RRR, RRS, RSS, or RSR. So for three stereocenters, you have a maximum of 8 possible stereoisomers, as long as we're not doing the identical substitution, which might cut the number of possible stereoisomers down if one of them happens to be meso or achiral, because then its image will be identical. Anyways, the maximum number of stereoisomers for a molecule that has n stereocenters is 2 to the n, where n is the number of stereocenters. Of course, like I said, that's just the maximum number of possible stereoisomers, and you might have fewer, like if there is one that's achiral or meso. So remember the definition of meso, a molecule that has 2 or more stereocenters, but that is achiral. So for example, how about this molecule, R2,3,4,5 tetrabromo hexane? In this particular stereoisomer of it, we've got the 2s, 3s, 4r, 5r, tetrabromo hexane. We are achiral meso. You can see there would be a internal plane of symmetry in this Fischer projection that cuts horizontally across the middle of the compound. Of course, you could convert this to bond line structure. I don't know if you remember that procedure from the last video. I guess we could review that here. But when you make a bond line, all you have to do is make sure you have the same stereocenters, right? SS and RR. So it's a process of unwrapping the molecule, right? So I just turn this Fischer projection to the right, and again you can assign stereocenters, priority 1, 2, 3. It looks like R, but it's really S because our lowest priority hydrogen substitution is pointing up. Same thing here, priority 1, 2, 3. It looks like R, but it's S because our hydrogen is pointing up. This one looks like 1, 2, 3. That's our fourth priority. It looks like S, but it's really R because our fourth priority is pointing up. Same thing here, 1, 2, 3. Fourth priority is pointing up. It looks like S, but it's really R. And this would unravel to this particular bond line structure, which we have drawn up there. And there's a procedure that you can do for unraveling it, or like I said, you can simply draw it unraveled and make sure your stereo centers are consistent, two S's and two R's next to each other. And the mirror image of this bond line, you could draw an axis through the middle of the molecule horizontally and rotate it 180 degrees, and then you would get something that's superimposable. And that may be more difficult to see on the bond line than simply seeing that there is a plane of symmetry, an internal plane of symmetry in this Fisher projection. So I guess Fisher projections do have their uses. So we will continue on. How about this SSSS stereoisomer? Well, I don't see any internal planes of symmetry. This is indeed chiral. So, you know, you could draw a mirror image, which would be the RRRR configuration. How about the SRSR? It's pretty easy to see from this Fisher projection that there's an internal plane of symmetry, so we know it's achiral. Since it has 4 stereocenters and it's achiral, we know it's a meso compound. Again, you could you know, do the whole procedure where you reflect its bond line structure in a mirror, and there's some way you could rotate this to get it to all superimpose. I would suggest, again, drawing an axis horizontally through the middle of the compound and spinning it 180 degrees, and it will superimpose back on the left, the bond line structure on the left. And how about this SSRS? Well, there is no internal plane of symmetry in this Fisher projection. It is chiral. And you could prove it to yourself drawing bond line structures, and yes, this is indeed a non-superimposable mirror image of our SSRS configuration. So practice is something that's very useful to master, you know, facility with bond line structures and Fisher projections. So that's something I urge you all to do, and of course attend the class time sessions, and we will undoubtedly have practice problems and exercises to work there. So in the next video recording, we'll sort of take a last view of Fisher projections, and then we'll move forward to the next class time.